Okay. So, welcome to Florida. I don't think we have any tornadoes scheduled for today. I'm going to be a little bit redundant here with some of the other talks, but I want to think of data acquisition as starting, say, at the sample. So not necessarily what physics you're using to transport or magnetization or what your detector is, but once you start with wires, then I'm getting interested. So that's sort of this physical measurement thing. And data acquisition doesn't really truly end until you have a graph in your whatever publication on the archive ready to go to reviewers. So I'm not going to talk too much about the end of that process. I'm going to focus more on the beginning of it, because I think there are lots of resources for making graphs and that sort of thing. But here's the sort of the rough outline of the talk, where we really kind of stop halfway through here. All right, probe wiring. You've heard this in at least 3 talks already, but I'm going to give my take on it, and hopefully the more times we tell you the same thing in different ways, you'll pick up on it. So what we're really going after here is fighting interference, not so much the intrinsic noise modes, but how the welders next door are conspiring to destroy your data. So okay, I think of interference in very electrical terms. So I reduce everything down to capacitors and inductors, and wires have some resistance. So, all right, any 2 pieces of metal in this room have some capacitance with each other. Say the eagle on the top of that flag and the point on the Florida flag, there is some actual capacitance between those 2. It's going to be really small. For those 2, it's going to be really small, down in the sub-femtofarad range. But it exists, and if you bring them close together, the capacitance goes up, so they can interfere with each other. Everything that conducts current has inductance. So let's see, what is something that's conducting current? Well, we have current being conducted through the fluorescent lights. So that's a current, and we have any number of things that could be sitting on your desk that will definitely see mutual inductance with that current in the lights. Fluorescent lights are a problem. So what I just described is actually mutual inductance. So you have 2 inductors that can talk to each other through the magnetic field. Self-inductance, which I should have mentioned here, was if you have just a conductor, current is flowing through it, it will attempt to not change the value of its current very quickly. So this really does apply to, oh, I'm making a transport measurement. I'm going to wire this side of the sample over to that side of the sample. Say I'm doing a Hall effect measurement. There's this whole problem with Hall effect measurements where you have to make this loop around the sample in order to get the Hall voltage from the opposite side. This loop has inductance. If you're trying to go fast, especially in pulse field, that loop is a problem. Okay, so let's take this sort of E&M view of it. These are 2, you could either think of them as charged rods extending infinitely in and out of the screen, or rods of current. The math works exactly the same either way. Pick which one it is and realize that the other one's the same. The important thing is that they are rods, so the radial dependence of the field is 1 over r, not 1 over r squared. So when you have something that's not infinitely long but short, and you have a 1 over r squared or something closer to 1 over r squared dependence, things get even better. So I'm showing you the worst case scenario here. And what I want you to notice is, let's see, it's not quite as, the whole screen isn't quite as red as it should be. It's better on the laptop. But look at the size of this field extending from the rod. The rod is sort of 3.5 pixels radius down here. And that one's exactly the same. But look at the size of it, and then I'm going to push them together. I'm going to try to push them together. No. Okay, let's do it this way. Let's bring it back out into keynote. And sorry, this is not quite as good as it should be, but now I'm going to push them together. And here it comes. Watch the size of them as they get close together. Right at the end, it shrinks. So all that field that was around it down here, that field is now much smaller. So by getting the two wires closer together, you're actually decreasing the field in the vicinity of the wires. Okay, so think about this. If you have two wires that are more than, everything scales with the diameter of the wire. So if you have a wire here and a wire here, their fringe field is large because there's some inductance between them. You've got a current going this way and a current going this way. That forms a loop. So if that current loop is large compared to the diameter of the wire, you've got not so much radiation, but near-field magnetic field around them. Or for voltage, it works the same way, a near-field electric field. So you need to get your wires sort of on the order of within a wire diameter of each other, to a factor of 3. And I'll show it to you again so you know what to look for. When you get it within about a wire diameter of each other, the fields extending around them shrink. There they go. Okay, so if that's not a good argument for tightening up your open loops and getting everything really small, I don't know what is. So let's go back to the presentation. Oh, okay. Awesome. There you go. Third time. Computers. Okay. Now, what is ground? You've heard this from, again, at least 3 presentations. I hate the word ground because I really don't know what it means. And I think about this all the time. To me, ground is anything that's actually at 0 potential, which is basically, we define the Earth as being at 0 potential. So, okay, the surface of the Earth is 0. Everything else is something slightly different from ground because we have to connect something resistive to it. Even a really nice long ground rod is not quite at ground. And if you raise the frequency up, remember everything that conducts current has inductance. So as you raise the frequency up, it gets worse than your half a milliohm ground rod because now it has inductance. So now it's, if you go to a gigahertz, you're definitely not at ground. You're hundreds of ohms away. And hundreds of ohms is definitely not a good ground. So okay, ground is ambiguous. Think of the complete circuit. And a lot of times, when we make up instrumentation, especially fairly slow instrumentation, we hook up the signal wires, and then we let the ground just flow back through the case. Well, that's a pretty bad ground. And maybe it's made of aluminum that gets bolted together here or there. Your ground current path matters because whatever the current path is, not the path that you possibly made for it, but the path that it actually chooses to take, which is the lowest resistance, lowest inductance path, is the path that determines the inductance. So if you've made the current go straight through your instrument and then flow all the way back around on the box, you've made a high inductance, and everything is going to slow down. And furthermore, if it's going on the outside of the box, then that's also the part of the instrument that's supposed to reject your interference. So now not only are you making it go in a big circle, you're making it go in a big circle and run through the interference gauntlet at the same time. So think about the path that the current actually takes and try to keep it from coming back along your interference shield. So okay, shield versus return. The shield is the thing that doesn't have your return current on it, or shouldn't. So you want to enclose everything in a nice metal box and keep the interference on the box. And then inside of that, you want to have your signal and your return, however you're going to arrange them, which depends on frequency and everything. So a circuit is, well, the probe wiring is a circuit. It doesn't look like a circuit board, but it is one. And you think of maybe a cable shield as the box enclosure. It just happens to be very long and sort of quasi-one-dimensional. So how you arrange the electric and magnetic fields that form your cable matters. And I tried to condense this into a flowchart. This is not a foolproof flowchart, but it's the quickest version I could think of that lets you answer the question, should I use coax? And usually the answer is no. but we use coax for everything, right? We plug a B and C in and we say we're done. That's very often the wrong thing to do. So the first question you have to ask yourself is one side of the signal grounded? Because if it's not, you really shouldn't be using coax. So if it is grounded, you have to be thinking about things like ground loops. So often the best thing to do is to actually design from the very beginning to say, let's not ground one side of the signal. Let's make them be differential. Let's make one be positive voltage and one be negative voltage. So if you choose to go with one side grounded, that's obviously the shield for coax. So now we ask, are we above a megahertz? And if you are, then great. You're really where you should be with coax. Because, let's see. Yes. So then you can ground the shield wherever you want, because the inductance of a piece of signal deciding to come back along some circuitous ground loop path is too high, and the signal will choose to not do it. So once you get up to high frequency, ground everything everywhere, use coax. Happy. If you do have ground on your a grounded return, and you're below a megahertz, then you have this situation I just described with the noisy box, where the interference is going to take over the shield of the coax and disturb the return of your signal. That's not good. So this is when you use triax. So this is explicitly separating the ground and the return. So you have the core, which is your signal one way. You have the sheath returning the other way. And then you have a separate shield around all of that. So you're keeping the interference on the shield and off the return. The situation we live in most of the time here, because we don't want to deal with ground loops and such things, is twisted pair with differential inputs. So you've got your twisted pair, which you usually see in the instrument room as a gray cable with a banana connection on the end. Banana's not the best thing to use, but it's very plug and play. Be careful of loose banana connections. Oxidation on banana connections will give you really nasty results. But the rules for twisted pair, don't ground one of them, or else you get a different capacitance to ground from one and the other. And then if you're trying to go anywhere faster than about 1 kilohertz, you start to see phase shifts. You may ground the shield. If you don't, it's sort of kind of useless. At low frequency, it'll to some extent reject electrical interference, but it definitely won't reject magnetic interference anyway. The undergrounded shield will actually help if you're above a megahertz. So if you have a sheath over it and you're going really fast. This is actually how Ethernet cable works. The shield on Ethernet cable doesn't need to be grounded because you're working at frequencies of hundreds of megahertz. But in the lab, grounding the shield does help if you actually have interference. OK, I mentioned triax. I'm going to just toss a trick up here. It's I've actually never used it myself, but it's in why use triax? Well, you can configure it in interesting ways. So here's the problem. I have this triax, but I have a sort of a voltage only. There's really not a lot of current, so maybe I have some sort of detector. And I want it to go pretty fast, and I want it to be shielded, and all of these things compete with each other. So the trick is you take a buffer amplifier, and you pull off the input of the triax, or the center core, and you feed that back onto the return line, not the shield. And what that gives you is essentially no capacitance between the core and the return, because they're at the same voltage. So if the core decides to go up in voltage because your detector lit up, then as soon as the amplifier can see that, it'll put the return line right back at the same voltage. So that's a cool trick if you have say a higher voltage but no current detector. OK. How do we deal with different speed and different impedance signals? All right, this is where I wish I had a laser pointer, and I do. OK. So the world we live in here at the lab tends to be in here. And if you're doing two-dimensional science, some of these graphene projects, you may well be living here. So in the high mega ohm range and going fairly slowly. So if you are trying to go faster, this is when you have to start getting creative. So the easy case is you have sort of ordinary impedance signals, and you either do a little bit of impedance transformation, or you dispense with the idea that you have to run at a mega ohm input. Maybe you can run at a lower impedance input and just take that into account when you make your measurement. If you have a 600 ohm input and you know that your the output on your probe is a few hundred ohms, then you formed a voltage divider, and you can use the voltage divider equation to back out what the actual voltage was originally, and it lets you go much faster. So if you work in pulse fields, this is not possible. So you have to be working somewhere under here. If you have really high impedances, going fast is hard. It's really hard because everything's limited by an RC time constant. So resistance times capacitance defines the time it takes to change a voltage. If the resistance is a giga-ohm, that's a billion ohms. So now you need capacitance of less than a nanofarad. Well, at sort of on the order of 1 picofarad per centimeter for normal cable, you're fast creating something that's getting close to a nanofarad. So there are lots of strategies for dealing with that. If you want to go even faster, then you're looking essentially at RF. So everything becomes a 50 ohm circuit, and the design looks nothing like it does at a kilohertz. But you sort of capacitively couple everything, and you're making little waveguides on your circuit board or whatever. You can't really work at giga-ohm. So you have to do something funky like put a little piece of antenna near your device and hope that you have enough voltage to get it to hop over. OK, so we have reached the top of the probe. So now let's think about how we turn our analog physics into something digital on the computer. The usual way to do this is an analog-digital converter. And there is one particular design for these things has really come out in the last decade. And that's the sigmadelta modulator. And this is important because it really actually influences what you buy, how you try to get the analog-digital converter that meets your needs. I bought one a few years ago that claimed to be 14 bits. And so naturally being curious about it, I hooked it up, and I fed it a signal, and I was getting 11 bits out of it. And I was really not very happy. Turns out it was a sigmadelta modulator, and somewhere deep in the fine print, like the back of the manual, it turns out that it said that you only get 14-bit below a certain speed. And I was trying to run it at 50 megasamples a second, which was its highest design speed. And that's why I was getting 11. So you have to drop down to like below 10 megahertz or something to get what it says it is on the box, which is really annoying. But here's why. A sigmadelta modulator starts from really a 1-bit converter. So a 1-bit converter says if the signal is greater than 0, I'm going to return a 1. If it's less than 0, I'm going to return 0. And on the digital side, you can figure out how to scale it and do all of these things. But here's how it works. Analog signal comes in. Now there's a loop here, so we have to presuppose that we have something else already on this side. So it does a subtraction. So if the thing that's come back around from the output is not correct, you get either a little signal positive or a little signal negative. And the key is that you integrate it. So if it's wrong for a long period of time, then you're going to get a bigger signal. So that signal gets fed into a 1-bit ADC, which says if it's greater than 0, I'm going to go low. If it's greater than 0, I'm going to go high. If it's less than 0, I'm going to go low. And then that goes into some digital filter out the end that we won't worry about at this point. But the important thing is that that bit stream gets fed back into a digital to analog converter and into our analog input. And if it's sort of guessing right more often than not, then the output of this integrator is going to stay close to 0. So as your signal goes a little bit up, this 1-bit ADC is going to go positive, and the filtering will take care of it at the end. If your signal is going down, then the 1-bit ADC will decide to go down. This is obviously a slow operation, because if you want a 16-bit conversion, you have to wait 16 of these cycles. So that's what was biting me with that supposed 14-bit digitizer, is that it wasn't actually designed 14 bits faster than 50 megasamples a second. It was designed, what they put on the box wasn't quite what you get. The benefit is that if you're going really slowly, a sigmadelta ADC can really make high-quality data. And that is what gets done in a voltmeter. So on a voltmeter, you get the choice of how many bits you want versus speed. So you take a 6.5-digit standard DMM, and it's going to work fairly slowly, sort of in this 10 hertz limit. You could go even slower and maybe get a few more bits. But as you start asking it to give you data faster, it will insist on giving you fewer bits. It's because the ADC can't keep up, because it has this sigmadelta configuration. OK, on the topic of bits, if you are, what time is it? OK. If you are digitizing something at 14 actual bits, not 11, you're going to get a much better signal than if you're digitizing it at 8 bits. So here is, these things are offset up and down. But here's sort of a 14-bit signal that maybe has just a little bit of noise on it, as the output filter of the sigmadelta isn't totally perfect. The 8-bit version has maybe proportionally the same size up and down, but it's all scaled up by, well, 14 to 8 is 5 steps. So that's 2 to the 5 is a factor of 32. So every time you add a bit, you get a factor of 2 better data. That's actually pretty powerful. Sure. So that you can see it. So we shifted it a little bit. And same thing in the FFT, where actually, no, not the same thing in the FFT. The 8-bit data is actually crappier than the 14-bit data, all the way across to high frequency. OK, other things that can bite you in a digitizer, and feel free to ask questions. It's fine. Other things that can bite you in a digitizer. Say your signal is faster than the digitizer's input rate. It doesn't do what you think it might do and just give you a 0 result. Because typically these things sample very much instantaneously. You might only get a fraction of a nanosecond of gating. And whenever that gate hits, that's the value you get. So let's see. If you have, so this is the sort of a worst case scenario. You have a sine wave coming in, and you have a gating here and here and here. Even though you have a sine wave, the output is DC. OK, that's bad. So here is sort of the best possible worst situation. And that is if your sample rate exactly matches the input wave. This is called the Nyquist frequency. So if you try to sample any faster than this, you're going to see what appears to be a lower frequency signal, even though, sorry, if the sine wave's coming in faster than that, you're going to see a lower frequency signal, even though the signal itself will actually be slightly faster than the digitizer. And so that's what happens in this case. The digitizer can't quite keep up with that sine wave, and so what comes out is this low frequency triangle. And that's illustrated in sort of a really crazy way, which does actually work. in this picture. So you pull off that point and that point and that point. And these things are sort of separated pretty far on the sine wave itself, but you're going to get some frequency out. So essentially, draw your frequency on one axis and signal level on the other, and pick a frequency input as long as you're below a few gigahertz, and you will get some sine wave out for some sine wave in, and they will not be harmonically related if your frequency gets too high. You can actually use this, and in fact, I was doing a measurement just a few weeks ago with ultrasound, where I had a 100 megasample a second digitizer, and the actual frequency was something like 150 or 140. And I said, okay, I just hooked it up and let it take, super sampled. Put down in my notebook that I did it, because otherwise the results would be flipped over in frequency. But it didn't take any effort on my part to use this to collect data that was actually faster than my digitizer. There will be, in many cases, amplitude reduction, because oscilloscopes and things have front ends that try to cut off the signal when you go above their limit. All right, now that we have our data digitized, we need to get it onto our computer. And so digital delivery has nothing to do with Amazon.com at the moment. OK, this is a chart thanks to Scott Hannes. Actually, most of these slides are thanks to Scott Hannes. These are all sorts of ways of moving data around the computer, not all of which are applicable to us. But how fast can you really go? Well, Thunderbolt, which is how the video is going from my computer into the projector right now, Thunderbolt's really fast, and it has very low latency. It's great. But you will never find a Thunderbolt connector on the back of an oscilloscope. Well, except for maybe video, actually. That would be nice, but they don't do it. So what will you find? Oh, you'll find some USB. I don't know if there's USB 3 yet, but you'll find USB 2. USB 2 is pretty fast. It also has pretty high latency. And sometimes the operating system, as we found out, will add extra latency, as much as tens of milliseconds sometimes. So the problem is not always limited by the hardware itself. It's often limited by who wrote your operating system and what decisions they made. Down here, come all the way down here, we have GPIB, which is quite slow. But the key with GPIB is that it can turn around data really quick. So OK, what are we looking at here? We have bandwidth. So this is just speed. How much data can you push over the bus at a time? And then latency, which is how fast do you get it after you ask for it. And well, let's see. We know that Ethernet is slow because the internet is slow. And well, PCI Express is pretty quick. This is what graphics cards are made of. So if you need to push video data, you're pushing a lot of pixels really quick. And then GPIB lives in this sort of slow speed but pretty fast latency. And then USB is slowed down by needing to form things into little packets and then send them out one at a time. So interestingly enough, if you take GPIB and you run it on the USB bus, you get this speed with that latency, or worse, because it has to sort of pass from stage to stage. But that's where we are. OK, so I'm going to go through some of the protocols really quick. I'm not going to spend a lot of time on these. Serial is still very much alive. In fact, it tells us what the field is, from the power supplies to the control room to the magnet cells. And it's doing it over fiber optic. But it's RS-232 style signaling. There is no standard called RS-232. It's kind of a free-for-all. Roughly, you indicate that there's something coming down the line, then you feed 8 bits, and then you indicate that the line is free. That's sort of all there is to it. So this is how we can bootleg it onto fiber optic and then onto something else, and then people make chips that convert it to USB. So that's serial. The latency on serial is very fast. which is why we use it to communicate field to the experiment computers, because we don't want any delay in creating the field with the power supply and telling you what it is. That's why we use it. GPIB. Oh, boy. It's really old, but it still works. And it has some nice features, like its connectors don't fall apart. Well, they do fall apart, but the connectors don't fall out of the back of instruments if you bolt them in. Whereas with USB, and I think everybody's probably knocked a USB cable out of the back of an instrument and lost data. I do it pretty much as often as I use USB, which is as little as possible. Sorry, there we go. There's our USB. And you know, you need a separate driver for every device, as opposed to in GPIB, you ask the right question and it answers you, whether it's a Keithley voltmeter or an HP or whatever it is. Okay, Ethernet. There are a lot of devices that are doing Ethernet now, and I don't understand exactly what the end strategy is, because Ethernet has no real protocol associated with it. So do you make an instrument into a web server? Do you open up a specific TCP port? Everybody does it differently, so it's really hard to standardize, and it's slow. But we have to live with it because we have a lot of these devices that are using Ethernet. The point is, let's see, I guess that's the next slide. The point is that we don't have a good standard for instrumentation anymore, because GPIB, it really should be replaced. It's old enough to be replaced, but none of these really mainline standards are meant for instrumentation. So we need to, somebody needs to come up with a good way to do this. And you folks doing science are a good place to start. Okay, so now, let's see, where are we? We've taken the data up the probe into the digitizer. We have bits. We've transferred it into the computer. And now what do we want to do with it? Well, something. And that something is totally dependent on you, and therefore you have to write it. Or when you're here, we can write some of it for you. But we use LabVIEW for this a lot. Okay, so who in the room has used LabVIEW? Everybody who's a user here should say yes. Who has written LabVIEW? A little bit smaller. Okay, that's fine. So the idea with LabVIEW is that you're programming graphically, which in some ways makes it easier, in some ways makes it harder. You can certainly see what simple programs are doing immediately. I think most people could guess what this does. And we say we're going to iterate n times, where n comes from some number we input. And then we're going to take that number and multiply it by 10 times out it comes in an array. So simple programs are really easy to tell what's going on. More complicated ones, maybe, maybe not. LabVIEW has a lot of things going for it. It's very modular. You can reuse things very easily, and you can move a lot of data fairly quickly. So I said that every user of this facility has used LabVIEW because that's the DC field data acquisition program. This is Scott Hannes' gem, and it pretty much talks to everything that we have in our instrument shop. So if you pick up an instrument from the instrument shop, bring it into the cell, hook it up, click this configure button, and it will say, oh, I see a voltmeter, and it's on GPIB address 6. And then you click on it, and you say, I want that one. Exactly how to use this, I'm not going to talk about it, but your user support will. And let's see, is there anything else to talk about here? No, I'm going to let your user support tell you how to use this thing. I'm going to talk about what's inside of it a little bit. So this is a plug-in architecture. So this is the VI for temperature controllers. This is behind the scenes. You don't see much of this. Actually, you see this piece of the screen. That's only because we show it to you. But the rest of this is going, and in this case, it's finding out what all the temperature controllers are that are attached to the system. So if you attach a couple lake shores, a 340, a 370, some old Neocera temperature controller, it's going to find them all, and it's going to tell you what they are, and it's going to let you get all the relevant parameters out of them. This is for temperature controllers. There's another module for voltmeters. There's another module for lock-in amplifiers. And more can be added. So if we buy another instrument, all we have to do is write another VI. Actually, we'll copy and paste this into another VI and modify it. OK. What else is happening? Let's go even lower level. This is a bit of the really key LabVIEW code, because this is what makes every GPIB request goes through this. And this is about the most debugged piece of code that there is. I think Scott's been tuning this thing for, I don't know, what, 30 years? Almost 30 years. Not quite. Yeah. So all of these little stops and checks and timing bits and resets all take care of a specific class of instrument that behaves somewhat badly. And this is kind of remarkable, because with GPIB, every manufacturer has decided to do things a little bit differently. And so the challenge of having a single VI that talks to every GPIB instrument, including Oxford power supplies, which are particularly nasty, is really quite the trick. But the result of this is that if you grab this VI and you call it with whatever data you want to feed to an instrument, and it gives you that data back, it can talk to pretty much everything. I've thrown it certainly a lot of instruments that Scott's never seen, and it tends to deal with them pretty well. It asks them the right questions and figures out what they're giving back. It also locks the resource, so that if you ask a question to a voltmeter, you don't accidentally get a response from another voltmeter or a temperature controller or something. This is buggy because instruments are buggy. I know certainly there's the known issue with the big temp display and the data acquisition at the same time, and we're still banging on it. I think the problem, they lock up against each other and then one of them crashes. The problem is somewhere in the temperature controller, I think. OK. So I'm going to skip through exactly which part does what. And I'm going to tell you that Scott's thought about this a whole lot, and it should work. OK, producer-consumer loops. This is a bit of an aside, but if you are somewhat experienced in LabVIEW programming, you should start thinking about these as sort of the next thing you should learn. Producer-consumer loops move data around very quickly and very efficiently. So the idea is that, OK, so this code is actual real code. This runs the resistive magnet protection computer that sits in the corner, and you probably shouldn't touch it, because if you wiggle the mouse too much, you'll slow it down and it will trip your magnet. Its job is to watch the magnet. And I guess some of you experienced this in Cell 9 when the welders drew an arc and the magnet protection system didn't like it very much, and so it tripped the magnet off. It said there's a voltage spike. This is bad. That's this code that did that. So let's see, what's going on here? We open some files and read in some parameters, and then we create this thing called a queue there. And a queue is just a data structure that lets you push stuff into it from one side and then take it out from the other side. Think of it as a pipeline. And so this block reads whatever is going on with the resistive magnet, makes decisions about whether to keep it running or not, logs a little, actually it does not log data. It just watches the magnet. And then it shoves some data onto this queue right here. Well, meanwhile, and it does this very fast, as quickly as it possibly can. Meanwhile, when the processor has some extra cycles, the queue gets read. And whatever's in it gets put on the screen and dumped to disk. And if you're sitting there moving the mouse, then the processor is busy, and it's not going to do this, or it's going to try not to do this. So this is a way of moving data around quickly and in a time-sensitive way. So you're always checking the magnet. That's the most important thing. You're not always writing to the screen in disk. That can come later. Oh, and I showed you each of those blocks. OK. So let's move on to what you do with your data. And I'm not too far from the end here. So you're going along. You're taking some data. And this never happens. What angle were we at last magnet sweep? What temperature did we start at? So you need to write things down. And there are two strategies that I like to follow. One of them is the log everything strategy and take pictures. Cell phone cameras make this great because they timestamp you. So anything happens, take a picture of it, log whatever happened, keep the data acquisition program running all the time. These are strategies that are made available thanks to disk space, right? We don't have to worry about disk space. So record everything. OK. So the file name strategy we use for the DC field program is based on an age-old VI called filer. If you use LabVIEW, it's a wonderful thing to have because you say, open up a file with this template, and it will open up that file. And if that file already exists, it will add a serial number to it. So you want to start a new data file, and you don't want to think up a file name for it. You call the filer, and it will append the serial number. And you write down what that serial number is in your notebook. 3 numbers, done. So you should be consistent with your file naming and make use of filer to generate your serial numbers. OK, so the second side of doing your data collection is that you should try to organize it as you're going for analysis later. You will usually have some idea what you're going to do with it later. So while you're recording this whole data dump, also write down things that are going to be useful and organize when your file starts and stops so that you can feed them into your analysis program in an easy way. Because you get to the end of the week, you go, whew, I have all my data. And then you have to pick it back up again. And it's a whole lot easier if you pick it back up again and everything is sort of organized in the right form. And maybe you have to do a couple of magnet trips to really get to the point where you believe this. But if your data is a mess, you're not going to read through it. And you're going to miss things that should be in your publication. So write down everything. And we have this question now of how do we deal with paper data, so what gets scribbled in the notebook, versus the data files that come out. And some people are even using digital notebooks now as well. We have to figure this out. And you have to figure this out, and then come and tell us how we do it. So here's an example log file. This actually comes straight from Scott Hannes, but I have personal connections to both of these pieces of data, strangely. This is a log file, just sort of handmade in TextEdit. So there's a file serial number. There's what was happening, was T sweeping or B sweeping. And then what did we change exactly? Say what was the temperature, whatever this parameter is, and some comments. That's a pretty good way to keep track of what's going on. It's concise. It's right there on the computer screen. The only change I would make to this, if it were my data, is I would organize these things in such a way that I could have a program read them. So maybe I would standardize exactly what this format looks like, maybe with the arrows, or maybe I wouldn't use arrows at all. Maybe I would make 2 columns, start field, stop field. I would come up with some way to feed it into a program, because ultimately, I like to do all of my analysis automatically. So I write programs, and you start with the original files, and you just generate intermediate analysis files until you're done. If you need to take a derivative, that goes in either a new file, or if you're using Igor, a new data set. What that gets you is that at the very end, when your advisor says, can you change that, you don't have to go back and reanalyze every single piece of data from that whole experiment by hand, because you say, yes, I can change that, and you change the parameter, and you rerun the program. OK, Renee is asking me to stop, so I'm going to leave the interpolation and change of basis slide for somebody to come up and ask me later. So resources, Keith Lee has a wonderful handbook on low-level measurements. I think Scott Hannes probably helped write it, I would guess. SRS lock-ins, you've heard about them. The application notes are just as good as Matt's talks. And the National Instruments has, and this is just one white paper on how fast you can move data around, but they have lots of information on data acquisition. OK.